Okay, good morning. So, we still want to continue the topic of combinatorics, but it's still with permutations yet. I don't remember. You remember that checkerboard that we were talking about, that aunt visiting the cousin and go to grandma? Do you remember what was the dimensions of that checkerboard? And I don't remember exactly what was the dimensions, but
8 and 5.
8, 5 and
8.
okay, 5. So I just want to refresh your memory. Okay, and then here. So do you remember I gave you one point in the middle? What was the coordinates?
Somewhere
Here?
a little to the right.
This one?
Probably.
Yeah?
Maybe.
Okay. I just want to keep it exactly as before. Okay. So let me call this point A. Okay, even though that might be, let me solve it from the beginning. Okay, this point we call it B, and this point we call it C. We know that the allowed moves in each step is either one step to the right or one step up. And then we want to see in how many ways, let us refresh everything here. In how many ways we can go from A to C. So let me put another point here, D, as well, to solve more problems, yes? Okay, if I want to go, forget about B and D for the time being, I just want to go from A to C. In how many ways I can go from A to C, provided that I'm allowed to use either this move in each step or that move. We learned that in order to go from A to C in any way that I want to make this trip, I have to go 1, 2, 3, 4, 5, 6, 7, 8 to the right, and then 1, 2, 3, 4, 5 up. Yes? It doesn't matter how I choose to go. I can choose, for example, to go in this way. I can choose to go in that way. But in any way, when I reach to C, it means that I have moved 8 units to the right and 5 units up. Yes, the only thing is that I can use different arrangements of these things. So instead of counting this problem, I would consider this problem that I have, for example, let us show R, use R to denote to the right and use U up. And then I have 8 R's and 5 U's. Yes, for example, if I give you this code, R, R, U, R, U, U, and then, for example, R, 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 and then I have U, and then I have R, 1, 2, 3, 4, and U, and R. So that is a code consisting of 8 R's and 5 U's. Yes, I have just arranged them. But this code can be translated into a road from A to C if we know the convention. The convention is this. So I go 2 units to the right because R appears 2 times. So it means that I start from here, go here, and then 1 unit up, I go here, and then 2 units, 1 unit R, and 2 ups, yes, and then 3 R's, and then 1 up, 1 R, 1 U, 1. So this road is actually coded by this the string of R's and U's, yes? And it is clear that each code like this corresponds to exactly one road, and one road that I have corresponds to a code similar to this. So this means that instead of counting the roads, which is a little bit geometrical problem and hard to see. Instead of counting those, I can count the number of strings like that. But we also learned how to do that. If all of them were distinct, then because I have 13 objects, the answer would have been 13 factorials. But now we know that still we learned how to do it, and you don't need to justify it in the exam, because that's, I will call it a standard. So then you say that, okay, I have 13 factorial, but this time 8 of them are of the same type, r. So I would put an 8 factorial in the denominator for the repetitions of r, and then I have 5 factorial for the repetition of u's, yes? And you really don't need to justify this. Okay, so you don't need to justify this in the exam. Okay, so is that clear? That's the total number of rows. But let us solve this problem. Assume that I want to count the number of rows from A to C with the same circumstances, but I am constrained to pay a visit to point B and then go to C. Yes? Okay, then in how many ways I can do this? I can see this problem as a two-stage problem. Stage 1, the trip from A to B, but the task, the goal is to go from A to C. It is not accomplished yet. One stage of the task is accomplished. I left A and I am in B now, and after that I have to go from B to C. That is the second stage of the problem. Yes. So in how many ways I can go from A to B? Actually, that is exactly the same problem with lower dimension checkerboards. Yes. That's exactly the same thing. How many R's I need? 1, 2, 3, 4 R's I need. 2 U's I need. So this problem, in this way, I can say that I have in total how many objects? 4 R's, 2 U's, so it is 6 factorial. But 4 R's, I have this, it becomes 4 factorial, and then 2 U's, I have 2 factorial. So this is the number of ways that takes me from A to B, but the task is not accomplished yet. I am in B now. I want to go from B to C, and that is exactly another problem of this type. So 1, 2, 3, 4, 1, 2, 3. So in total, I need 7 moves, 7 factorial, 4 factorial, and 3 factorial. And I hope that now you're not confused at all, that I'm not allowed to add these two numbers. We have to multiply them, yes? Because if I do this one, the task which I have to go from A to C is not accomplished yet. This is not, so I have to multiply it. And then you really don't need to simplify that much unless it's stated in the problem. So you can just write this. Is that clear? Okay. Now, for example, let us solve this problem. So assume that you want to pay 2 visits, one at B, one at D, and then go to C. Okay, then how can we solve that problem now? I want to go from A to B, and then, of course, I have to go from B to D, and then I have to go from D to C. So in how many ways I can do that? From A to B, that's the total number of ways. That's exactly written on the board. 6 factorial divided by 4 factorial, 2 factorial. Okay, and then what? I have to go from B to D. In how many ways I can do that? Of course, it is very trivial in this case. In how many ways? Yes? 1. Yes, because if I want to follow the rules, I have to go R and R. But if you want to solve it, how do you solve it if you want to use this formula? So you have 2 moves, then 2 R's. How many ups? 0 ups. You really don't need to write that, but I mean that even if you write that, you will get the same answer. And that is one of the reasons that 0 factorial by convention was defined to be 1. So that's a good convention, because otherwise I am not allowed to use. I have to change my strategy when it comes to here. But of course, you really don't need to write that. Even you don't need to write this 1, but I'm writing this to emphasize that I have considered that. And then I go from D to C, 1, 2, 1, 2, 3, 5 moves I need. And 2 to the right, 3 ups, yes? 2 to the right, 3 ups. Of course, it doesn't matter. And that would be the answer. Yes? Is that clear? Now, let me ask you this question. In how many ways I can go from A to C? That was one part of the problem which we didn't have time to finalize. I want to go from A to C, but of course it is very simple. In how many ways I can avoid B? I want to still go from A to C with the same constraint of moves, but I want to avoid B. Of course this is very trivial. So what can I do then? Okay, any ideas? It is simpler than that. It doesn't need negotiation at all, or discussions. I want to go from A to C, but I want to avoid B. So it means that I want to count the number of roads which are not passing through B. On the one hand, I know the total roads that will take me from A to C. On the other hand, I know the total roads that I have to pass through B. So then, yes?
I think 13 factorial over 8 factorial times 5 factorial minus what's in the box.
Yeah, exactly. Because the total, this number is the total number of roads that takes me A, regardless to C, regardless if I am passing through B or not. Yes? This is the total number of roads. What is this one? These are the total number of roads that goes from A to B passing through B. A to C passing through B. And I want to now find the number of roads that goes from A to C, but they are not passing through B. I think that is not very hard to see. That's the complement rule, yes? So the answer to the question mark here would be, so the answer to this question mark would be 13 factorial, 8 factorial, 5 factorial, as Ruben mentioned, minus the 1 in the box. Of course, that is up to you if you want to simplify. But if I do not mention explicitly, that is completely okay for me if you just write that. Yes? Okay. So we don't have any problems with this now. Now let us think about another problem. So assume that I have 10 people. So 10, let us call 10 students. So I need, for example, 4. We have 2 projects, for example, one in physics, one in mathematics. For physics, we need 4 students for physics project, and we need 6 students for some reason for mathematics. Yes. And assume that all 10 students are eligible both for physics project and math. It doesn't matter. Okay? And then the teacher, for some reason, wants to have the choice. Okay? In how many ways that teacher can choose these students for this? For example, if you want, I can write student number 1, student number 2, up to student number 10. For example, one possibility for me to choose the students is to choose S1 to S4 for physics and the rest for math. That is one grouping, yes? So in how many ways I can do this grouping? I can write for example, let me write physics here, mathematics here. One possibility is that S1, S2, S3, S4 is here, and for mathematics we have S5 up to S6. This is one possibility. By the way, I hope that you agree with me the nature of the problem. Do you think by the nature of this problem, the order of these students matter? The way that I express the problem is that you see that grouping is important, not the order of the student in each group, yes? Is that clear? Okay. But so this should be counted once. For example, if I write S1, S2, S3, S5, and then here if I have what is left, S4, S6, S7, S8, S9, and S10. This is one item that I have to count. This is another item because the grouping has changed. I am asking you in how many ways I can have this grouping. Yes, Ruben?
10 factorial.
No. No. So why do you say 10 factorial? Of course I have, the answer that I know is not this, but I'm still ready to hear.
I thought because 10 factorial, that's reordering them.
No, that's my point. When you say that you have 10 factorial, it means that you are considering all arrangements of the students, for example, in a line. Here, I really don't care. For example, if I start interchanging these students inside physics, I am not creating new groupings. Is that understandable? So the students in one group matters. If one student is a different student, then I consider this a new group. Is that clear?
Yeah.
That is my intention, even if I was not very good to express myself, but that's my point. So that is another word. I want not to use it because I will talk about that later. That is called combination. But for the time being, you really don't need to learn about combination to understand this problem. This grouping is one grouping and this grouping is another grouping, not because, for example, I can change these, not because you see that the grouping, the students participating in physics project in total is different from the students who were participating in physics project before. Whenever this happens, I consider this one new grouping. Yes, is that clear for everyone? Okay, now I want to solve this problem. In how many ways I can do that? Yeah, I want you to think about these problems. You see, these problems are very easy in nature to state, but might be a little bit hard to understand. So if you want to solve everything from scratch, this is why we have some kind of models. We should be able to use them as anchors, you know. Otherwise, the problems become hard. Do you find any connection between that problem and somehow arrange permutations with repetition? So here, when I stated this problem, apparently it was a totally different problem in the beginning. But by looking closer to the problem, we were able to understand the connection between this problem and permutations of objects in which some of the items are repeated. Yes? Now, can you imagine any strategy, any way that you can understand this problem in that way? Assume that you really want to do this. What do you do? Assume that you really want to do this. Try to see, because it is not possible, you cannot do this. You can just call randomly 4 people and say that, okay, you are for physics project and the rest is for the math project. This is possible. It is not possible that you cannot do that. Yes?
Okay. So, to comparing it with that problem, we would say that physics and math is the difference between choosing going right or up.
Yeah, exactly.
And then the number is same.
Exactly. So you see that when I state the problem, you need to find this connection. So for example, one practical way to think about it is that I take some cards on 6 of them I write M, yes, and on 4 of them I write P. And then I put them in front of the students, yes. The students getting the label M, they will go to math project. The students that they get label P, they go to the other project. Is that clear? So that's the same problem. Arrangements, you can visit it, you can view the problem in this way. I have 6 M labels, and then I have 4 P labels. Yeah, let me write them. M. Yes? And then I have students in one row. I just, for example, I can shuffle the cards and put them in front of each other. Then this is one grouping. Then I can start rearranging these labels. Then it means that the groupings are different. Is that understandable, that that's the same problem? But this is easier for us because we have an anchor and we know how to deal with permutations with repetitions. So the problem is exactly 10 factorial divided by what? Divided by 6 factorial, 4 factorial. That's the problem. That's the answer to this problem. Is that clear? Yes? Okay, now let us consider another problem. Let us consider 10 students this time. And this, I want 5 students for physics and 5 students for mathematics. What would be that answer? The reason that I bring it up is because of some reason, okay? So it's not hard. I just want you to think. 5 students for physics project and 5 students for math project. So what is the answer to this problem now? Yes?
I mean, it should be 10 factorial divided by 5 factorial.
It is.
By
Still it is.
factorial.
It should be and it is, yes. So this is 10 factorial. The only thing is that I have 5 M's and 5 P's and I want to arrange them in a row. But order matters. You see, this problem, in each grouping, the order wasn't a problem for me. But I translated this problem into a permutation problem. In the permutation problem, then arrangement, the order matters. But the answer would be, as you said, still 10 factorial, but divided by 5 factorial, 5 factorial. Yes? Now, let us try to solve this problem. 10 students, but I want to make them groups to compete against each other. Yes? So I'm not making a physics project, I'm not making a math project, okay? So let us consider this scenario 5-5 still. So I have 5 students for physics. Let us write it. So I want to group them into 2 groups, 5 students in each group. I'm not labeling the groups, yes? For example, I don't know, if you want to have a football match or whatever, I just want to split you into 2 groups of 5 to play against each other. Okay, so I just want you to solve this problem. And I hope that you feel the difference. Yes? Do you feel the difference? So I have 10 students. I just want to split them into 2 groups, each group containing 5. Is it different from the problem that I want to split 10 students to 5 and 5? One works on physics, one works on mathematics. First of all, let me try to motivate you that this problem is different from the previous problem. Yes? Because in this problem, I call the name of 5 students, I put them in one group. What does it mean? The rest automatically forms the second group. There is no first group, second group. Yes? In the previous problem, I not only have to choose my students, and then I have to label them. Are these students for math or physics? Yes? Because when I name 5 students, they come close to me and they ask, okay, on which project we are supposed to work. So you see, they have to ask another question from me to make it clear. But if we are supposed to compete in a football game or whatever, whenever I call 5 students, it means that I want to put you in one group. Then you don't say in which group you want to put us, yes? Is that clear? That these 2 problems are different. First of all, I want you to feel the problems are different. Yes or no? Let me just repeat. In the case that I have 2 projects, math and physics, I call 5 students to come forward, but they still wait to hear from me. Are they supposed to work on physics project or math project? Then I have to assign, in principle, after calling them, I can still choose them to work on physics, one option, or I can choose them to work on mathematics, second option. Yes, is that clear? But in the case that I want to compete, I want them to compete in a football match, the grouping just matters. So it means that when I call them, these students automatically know that they are in one group. The rest will be in the second group. They don't ask any questions. There is no other second options. I hope that I make it completely clear. First, I want you to understand the difference between these 2 problems, even though they are very similar. And then, of course, if you understand what is going on, might be you will be able to answer it finally. So the answer for the physics project, math project case was that 10 factorial divided by 2 factorial, 5 factorial, 5 factorial. This was for the case that I had a physics project and a math project. It means that my groups are labeled. Yes? So that was the answer to the previous problem. Using this understanding what I told you, can you use somehow this idea to solve the new problem? That just grouping matters. Groups doesn't have any labels. Okay, let me pause recording a little bit. Do you understand that there is a factor of 2 going on?
Yes.
Yes? Yes or no? Because I told you that when I asked the students for the first problem, when I group them in one group, then I have the 2 options. Either say them work on physics or say them work on mathematics. So it means that after the choice is done, the grouping is done, still the task is not accomplished because I have to assign them on which project they have to work on. How many options do I have? I have an option of 2, yes. So it means that there is a factor of 2 going on, but I don't want to answer the problem. You know the answer to the previous problem using that, and this idea might be you will be able to answer this one easily.
Ge dem varsin lön. Om de har gjort den första gruppen så är den andra gruppen automatiskt klar.
Det är inte det samma med förra.
Fast, nej, men han säger att det inte är det. Ja, men det är han sa. Han sa själv att när du har gjort första gruppen. Nej, men jag gör inte den delen.
No answers?
Ja.
Anyone at home?
Han sa ju att när du har gjort första gruppen så finns det...
It shouldn't be hard. Say something, yes? So I don't understand where is the hard part of the problem.
It just feels so similar to the last one, except
No,
instead of calling them math and physics, you just call them team 1 and team 2.
No, not team 1 and team 2. If you think in that way, yes, you are right. There is no difference. But there is no team 1, team 2 unless, for example, I want to group them and associate one part of the, I don't know, field to one group. So that is exactly the same problem. So here, that was, I don't know how to say, if you call them team 1 and team 2, might be that is different. For example, say that team 1 plays on Saturday, team 2 plays on Sunday. Then it means it matters. But here, I just want to split them into groups of 5 and then let us play against each other. So I told you, what I told you. So here, I asked the students, I name 5 of them, they come forward. I don't need to do anything else. I did my grouping. Okay? But in the previous problem, if I just call 5 names, they come forward, but the problem is not finished because they want to listen from me which project I am going to assign them. So after calling them and they are coming forward, still I have 2 options left. Either assign math to the problem to the students who are forward, or I can assign physics. But in the previous case, that is done. Do you agree with me? That is a very normal life, yes? If I want to choose, okay, 5 students they come forward, okay, let's play against each other. That's finished. But in the previous problem, it was not finished. So there is a factor of 2 somehow involved. But which one needs a factor of 2 times or divided by 2? That is, you need to say. First of all, do you understand the difference now or not? Not yet. In your brain, if you say team 1, you are labeling 1 to one group and 2 to the second group. Yes?
No.
That is, yeah, but...
Not anymore.
Okay, not anymore. But for example, if I want to say that I want to 5 students play chess and 5 students play, I don't know, backgammon, then that would be math and physics problem again. But this is no, I just want to choose 5 students then I say that, okay, now you compete against this group which is left. Is that understandable? I don't know how to explain more obvious than that.
6. Och sen så minus...
Du får jättemånga dubbla kombinationer.
Fast det är klart, jag säger ju när jag har gjort det. Jag har en plats.
Okay, let me make it again. Let me ask you one. So here, let me say you something. Here, consider the previous problem. I call it math. I call it physics. This is probably, you understand it better. So here, I put S1, S2, S3, S4, S5. Yes? And I put S6, S7, S8, S9, and S10 here. Yes? This should be counted once in the previous problem. Yes? But now look, what I do here, I write S6, S7, S8, S9, and S10 here. And I write S1, S2, S3, S4, S5 here. Okay, still think about the physics and math project problem. This item, I assume that I have listed all possibilities and I start counting them. This should be counted once. Agree or not? This should be counted another time. Is that clear? So when I count it, because even though the groupings are the same, but now these students from number 1 to 5 are working on math project, students from 6 to 10 are working on physics project. Yes? But now what is happening? Is this the same situation? Even though the people are in the same group the same, but these people are now working in math project and these people are working in physics project. Is that understandable? So if I count this once, I have to count this another time even though the combination of students are still the same, but the labels P and M are different. Yes? But now, let us clean the label. And I want to, they want to play football against each other. Is this and this should be counted 2 times or once?
Once.
That's once. I don't know how to say it. Do you understand that? Yes or no? So what is the result of this one? You say that these people are competing against this. What is happening here? Again, these people are competing against it. That's the same scenario. Okay? So now tell me, what is the answer to this new problem?
Previous answer divided by 2.
Divided by 2. Finally. Yes, that's final because every permutations of 2 between these two are now counted once. So I have to divide the previous number by 2. Yes or no? Yes or no? Okay, so if I have another question for you. Make sure that you really understand. So yes, the answer to this problem is 2. Divided by 2. So that is the answer to football team. And this without 2 is for math and physics project when I have 5 and 5. Yes? Is that clear? Yes or no? Okay, now let me make the problem a little bit different. Okay, let me ask you one question. Still I have the same 10 students. Okay, but now I have 5 different games. Game 1 up to game 5. I don't know because it is easier for me to write it. So we have 5 games. That in each game I only need 2 persons competing against each other.
2 persons.
Yes, like chess or backgammon, for example. Yes, all of these games are of that nature. Okay, my question is, how can I group these 10? So let me ask you in this way: how can I group? Yes, how can I choose 2 for game 1? 2 for game 2, 2 for game 3, etc. How can I do that? So not how is it wrong, how many ways I can do that?
Nej, men en person ska spela mot en person med 9 personer.
Is the question clear? I have 10 students or 10 people. I want to group them in groups of 2, but one group plays game 1, one group plays game 2, and etc. Okay, in how many ways I can do that?
Och sen samma sak här. En kör med 2, en på 6.
For me, this labeling is very helpful. You take a card, write something on it, and put it in front of the student, something like that. Just think about labeling, it is not hard. I told you, take 2 labels, write G1, G1. So you have 2 cards written G1. And then take 2 other cards, write G2 on them. Yes? And etc. So what's the answer? Don't write anything, just answer it immediately. What is the answer? What is the answer? Yes? Yes?
Is it 10 factorial divided by 2 factorial? 5 times.
Exactly. So why do you hesitate to say? I told you that you take 2 cards, you write them on 2 cards, you write G1 and G1. On 2 other cards, you write, G1 and G1, G2 and G2, and etc. How many cards in total? And then the students are assumed that you can imagine that the students are waiting in a row. And then you have 10 cards in your hand, and then just put 1 card in front of each student. 2 students will receive G1. This means that these 2 students are supposed to be in one group and playing game G1. 2 other students will receive card G2. It means that they are supposed to be in one group, not only in one group, but they have to play G2. They are in group, but they cannot play G1. They have to play G2 according to this rule. So then, how many items you have? You have 10 items, but not all of them are distinct. So it means that if I write 10 factorial, that is wrong, because 2 of them are of type G1. So I have to divide a 2 factorial because of the repetition of G1 2 times. And I have to divide by another 2 factorial because of the repetition of that, and then etc., the same thing. 1, 2, 3, 4, and 5. Of course, I would prefer to write it a little bit more compactly by writing this to the 5. That's it. So that's the answer. Is that okay? I don't know. Is it a little... I know this grouping problem. I don't know. Based on my experience, it's a little bit hard for students, but I try my best to explain as clear as possible. I don't know. Is that understandable? Yes or no? How many of you agrees what I have written here? Feel it with flesh and blood or something, what do you say? No, because I want to go to the next step. Just confirm that you are comfortable with this.
Yes.
Everyone, why do you think it's hard? Just imagine I have these cards in my hand. I want to assign them to the students. Yes?
Are they assigned to, in this answer, are they assigned to, like, on a chessboard, 1 black and 1 white? Or
No, might be that is my mistake. No, games. I didn't say anything. We don't know what's happening. Just games.
So just like pairs?
Yes, pairs of 2. Yes. Pairs of 2s, but labeled. Yes, is that clear? Might be, so you are thinking something, because it is not hard, might be that my explanation is not good. So let us assume that like this. We have 5 rooms with exactly the same conditions. Okay? Except that the rooms are labeled. Room number 1, room number 2, up to room number 5. And then I want to put, I don't know, roommates together. And there is no left bed, right bed. Don't imagine like that. Because otherwise you start thinking about which side I should go. No, just a box that you are supposed to jump in. Yes? I don't know how to say it. Don't try to think it in that way. But I have 1 box, as we call it room, and then I am supposed to put 2 students in room. There are 2 scenarios. Either the rooms are labeled, yes? So you see, this is probably a better example. I have rooms, but these rooms, inside the rooms, are completely symmetric with respect to the person that are taking it. Okay? Except the rooms are labeled. And for some reason, that is up to me to decide which students go to which room. Yes? Okay, so what I do, I write 2 1s on one card, 2 cards, and 2 2s on 2 cards, 2 3s on 2 cards, and etc. And then I put these cards in front of the people. 2 people will receive card number 1, they go and be roommate together. Yes? And the same thing for the other one, and the same thing. That would be the answer to this problem. Yes or no? Okay. So here, but now I want to make this problem a little bit harder. Is that clear? Now I want to remove the labels. Yes? I want you to answer this one. The same problem, but I'm removing the labels. But I want now to answer that one. If you can answer that, it means that finally you understood the problem.
Men nu står det ingenting. Det var ju där exakt samma fall. Då måste du dela den också.
When I remove the labels, it means that they are completely symmetric. This abstract way of thinking you have to learn in combinatorics. So you see, when the rooms were labeled, okay, let us see. I have a list in front of me. I call the name of 2 students. They come forward. Is the task accomplished yet? They are here, but the rooms are labeled. Is the task finished here? I have 2 students waiting for me. Is the task finished? The next stage is to assign a room to this group. Do you understand? So the 2 students are now here waiting for me to hear which room they have to go. Okay? Yes or no? Yes. But if I remove the labels, what does it mean? It means that when I read the names, 2 students are here, they can choose whatever they like to. There is no difference. Yes?
You divide by an extra 5.
No.
No.
But you are close. Okay, so let me tell you. So here, let me just imagine this is room number 1, 2, 3, 4, 5. When I start writing, you will understand. Student number 1, student number 2 here. Student number 1, 2, 3, 4 here. Let us be patient because this seems a little bit hard for you. And 7, 8, and 9 and 10. Is that understandable? This is for the labeled one. This is one grouping. Let me ask you one question. If I choose to put S3 and S4 here, and then S1 and S2 here, and then S5 and S6 here, and then S7, S8 here, S9 and S10 here, have I changed the combination of these groups? No. Still, S3 and S4 are roommates as before. S1 and S2 are roommates as before, and the rest as before. But now, S1 and S2 are taking this room. S3 and S4 are taking room number 2. But in this scenario, this is changed. Even though the roommates from combination point of view is exactly as before, but do you count this once and this one second for the first scenario, yes or no? If I count this once for the labeled rooms, should I count this once more or not? Yes. Is that understandable? Okay, can you imagine another grouping? No, the same combination of people, but different scenario. I can arrange them a little bit, yes? But now the point is that without changing these combinations, how many items I can imagine in which the roommates are still the same, the rooms are different, yes?
5 factorial.
5 factorial. So when you say 5, it is not completely right because that number is 5 factorial. Okay, now what is the answer to the problem without labeling? This one and this one are the same now. Because there is no labeling, what matters is grouping. Yes or no? Okay, then what would be the answer? That would be the previous answer. Yes? divided by 5 factorial. So when the rooms are not labeled, when the groups are not labeled, you don't have that extra division. But the rooms, when the rooms are not labeled, you have to divide, but by factorial number, not just by 5. Is that right? Yes or no? Okay. Is that clear or not? Yes. Might be when I express it in some language, you need to think in abstractly. In the abstract level, that is what I want to count. Whenever you yourself recognize this is your goal, you have to divide by factorial. If somehow you understand that they are numbered, these groupings are numbered. So it is like this. In abstract language, it is easier. So you see, in the previous problem, I have boxes, just boxes, labeled, yes, and I have 10 labeled marbles in my hand. So this is probably better. When I talk about games and grouping, you are confused. This is the abstract notion. I have completely identical, yes, boxes with labels, and I have completely identical marbles with labels. Yes? I have 5 boxes with labels 1 up to 5, and I have 10 marbles labeled just with 1 up to 10. Yes? Now you want to make them in groups of 2 and put them in the box. Yes? In each box, it doesn't matter if you reorder them. You just put them in the box. But grouping matters. Yes? In the first problem, this is the answer. It's abstract way of thinking. Yes? In the case that I take the labels out, then I have really 5 places, but they are symmetric. It doesn't matter. Yes? At the end, I want to put them in my hand and carry them. And then the order doesn't matter. Yes? So this is the abstract way of thinking about it. Okay, is that clear? Okay. Now let me ask you another question. This is called a cyclic or cyclic. Cyclic actually permutation. Okay, so what is the meaning of that? I don't know, somehow in the Combinatorics books they call about that I have 5 students. If I want to arrange them in a row, that is a little bit, I want you to understand the difference. If I ask you in how many ways 5 students can be in a queue, then you say 5 factorial. But now my question is that how many ways they can sit around the round table? Yes? Of course you might say 5 factorial, I can agree to some extent. But let me put a constraint. By a round table, I mean what matters for me are the neighbors. I don't care about the real position of a person in a seat around the table. What matters is that my neighbors are the same. If the neighbors of all the people are the same, even though they have, so let me tell you in this way. So let me make it by the way, 4, 4 is easier to draw, okay? So this is one seat here. This is one seat here, one seat here, one seat here, okay? And then I have 5 people, so let me call them A, B, so 4 people, so A, B, C, D. So when I put them here, A, B, C, D, this is one possibility. So assume that this you are actually looking at the round table from above, okay? But now look, I consider another scenario, the same table, the same seats. And then I give this one to A, this one to B, this one to C, this one to D. Yes? This one is completely different from this one. You immediately recognize the difference. Yes? You see the difference. If this matters for you, the answer is still 4 factorial. If this is different from this, if you want to have this different from this. Okay? But if I tell you that what matters for me is not the real seat that they are taking, the only thing matters is the neighbors. So if I ask you who are the neighbors of A, they are B and D. And I don't know, if you're looking from above, B is the left neighbor, D is the right neighbor. Yes? In this scenario, yes, if you look from above again, the neighbors of A are still the same two persons. Yes? And then the order is also the same. A, D is still the right neighbor, and B is the left neighbor. So you see, if the neighbors are important, this and that should be considered the same scenario. Is that clear? Yes? So now, can you tell me what is the difference between this, which we call it cyclic permutation, and, I don't know, straight permutation, yes? So what is the answer to this problem? 4 people, they want to occupy those 4 seats. The position is not that important. What is not important, what matters are the neighbors. If the neighbors of everyone, not just A, everyone remains the same, I do not want to consider it a different scenario, even though I can see this scenario is different. I can recognize the difference. Yes? But I want myself intentionally to consider this one the same because the neighbors remain the same. Yes, Amanda?
4 factorial divided by 4, so 3 factorial?
No.
Because there are 4 scenarios in which they have the same neighbor.
Okay, so you yes, your strategy is correct, but your answer was wrong. Repeat it again. Might be I heard it right.
4 factorial divided by 4.
Yeah, that was correct. Yes. Yeah, I heard another 3 factorial there.
No, but if you simplify it.
Aha, the answer was 3 factorial. Yes, that's correct. So yes, you are right. Why? Because you see, let us write it in this way. So here, let me consider this A. I start always from this one. This is A, B, C, D. If I start from the top and then so I go to the right, for example. This becomes D, A, B, C. When it comes to permutation, this and this should be considered 2 times because they are different, yes? The order here and the order there are different. Agree or not? But for this scenario, I consider them the same. So can you tell me how many names I can have for this if I give you A, B, C, D, or if I give you D, A, B, C? In the normal permutation, they are different because the orders are different. But for my case, they should be considered the same. Can you give me another name for the same permutation? Circular permutation. Can you give me another name? Yes?
C, D, A, B.
Yes, exactly. So let me write it, if you don't mind. Let me write them below each other. So the one that I wrote was D, A, B, C. The one that Kevin mentioned was C. What? Can you just write?
D, A, B.
D, A, B. Can you give me one more yourself?
And then the last one would be B, C, D, A.
Exactly. So these 4 items, if I just care about permutation as the natural permutation, they have to be considered 4 times.
Yes.
But now all of them in this scenario should be counted once. Agree or not? Okay? So then it means that, but now, can you give me another one which is really different? So these 4 names are the names for the same circular permutation. Yes? But can you give me another one which is different from these 4? A, for example, D, C, B. This is definitely different from that one. Yes? For example, the neighbors of D are A and C. The neighbors of D are C and A. You see, they are the same neighbors yet, but they are different order. Yes? And then for this one, how many names you can invent again?
3 more.
3 more. Yes? So it means that instead of, so I can write A, D, C, B, I can write B, A, D, C, I can write C, B, A, D. I can write D, C, B, A. Yes? And that is why, if I continue this, I will get a rectangle. Okay? The length I don't know. That is exactly what I want to count. But the depth I know is 4. On the one hand, the total number of items is 4x. On the other hand, when my rectangle is finalized, what I see is the all permutations. All permutations are 4 factorial. So this means that this number that I am supposed to count is 4 factorial divided by 4. And as Amanda mentioned, if you simplify, it becomes 3 factorial. Yes? So that is something I want you to know. Can you imagine what will happen if I have n distinct objects? I want to arrange them in a circular way. Can you guess what will happen? That answer was for 4. Now instead of having 4 objects, I want to have n objects. What will be the answer? N minus 1 factorial. Because what happens, instead of having 4 names for each, I will have n names for each, times x equals to n factorial. So the number that I'm looking for is n factorial divided by n, which can be simplified to n minus 1 factorial. So that's also one anchor in your hand. So if you want to have cyclic permutation of n distinct objects, it is not n factorial, it is n minus 1 factorial. But I want you to understand why this is the case. Is that clear? Yes or no? Okay, I want to move to the last part of permutations. And this is now, I want you to answer this question. If I give you this, let me try to understand it by a simple example. I give you A, B, C, D. So now, completely forget about circular permutation. We are back to normal permutations. Yes, I have 4 distinct objects. If I ask you how many permutations are there, you would say 4 factorial. But now I ask you, I don't want 4 permutations. 4 permutation means, this is another name, 4 permutation. Permutation. So when I say a 4, of course, I haven't used this terminology before, because when I ask you how many permutations are there, you would say 4 factorial. So that is, now I call it 4 permutation. I can also ask 3 permutation. How many 3 permutations are there? What does it mean? It means that I want you to use only 3 objects, not all 4 of them. But still, I want you to arrange them. For example, how can I solve this problem? How can I understand the problem? First, if I want to have a 3 permutation, I choose 3 of them, for example, A, B, C, but still arrange them. So I choose A, B, C, but in how many ways I can arrange these 3? 6 ways, yes? A, C, B, B, A, C, B, C, A, and C, A, B, and C, B. So each one of these that I have written here is called a 3 permutation. A permutation consisting of 3 objects. Yes? Okay, but this is not the only case. I have another scenario. I can choose A and B and A and B and D this time. But I can arrange them again, A, B, D, A, D, B, B, A, D, B, D, A, and D, A, B, D, B, A. Now assume that this is my goal, and I want to complete this rectangle. How many items will be there? Is that understandable? So I have more options available. I have to arrange them, so still order matters, but I have more probably. Yes? Of course, this is an exception. You might get the same number, but that's coincidence. But I want you to understand, if I finish this one, Yes? If I finish this one, I will have a big rectangle containing items. How many items you will see in that rectangle and why? Because this answer is coincidentally the same as before, but I want you to understand it. So what you want to count and you don't know is the length of this rectangle. Ah, sorry. Yes. No. Yeah, you need to understand it yourself. Yes, that was one. How many items are there? I give you a hint. Just go back to the first session of combinatorics. That is the product rule. Yes?
Isn't it 4 factorial times 4 factorial?
Times, no.
Plus.
No.
Divided.
Divided is correct. No, but not divided is also, that's also wrong. Yeah. No, I want you to understand. Go back to the first session. In principle, I could ask this question exactly on the first session for combinatorics. So when order matters, how many positions you have?
You have 4.
No, I want 3 permutations. And then they have to be labeled. There is no question should I label them or not. But because this is the meaning of permutation. In the permutation, always order matters. Okay, now can you solve the problem? I want to assign a letter to the first position. How many ways I have?
4.
I have 4 items, so 4. Stage number 1 is finished.
Then 3.
So this means that one of them, and then
3.
3, and then
2.
So the answer is 24 factorial again. I told you that this is coincidence. That is 4 factorial. So there is no division or whatever. There is a division. By division by what can you say?
What?
Division by 1, which is 1 factorial. Okay, let me ask you another question. How many 2 permutations you can answer? Can you answer this one? How many 2 permutations you have for A, B, C, D? Then how many boxes you need? You need 2 boxes. And then how many options are available for the first box? 4. How many will be left for me? How many options will be left for the second one? Is 3. Agree? So the answer is 12. So if I ask you how many 2 permutations are there, the answer is 12. How many 4 permutations are there? 4 factorial 24, and it was a coincidence. How many 3 permutations? But by the way, it was not coincidence. Do you remember we talked about Mississippi? I told you that there is no difference between permutations of 10 and permutations of 11. If they differ by 1, they are the same. Yes, and that's also the same thing. Okay, now can you answer this question in general? I give you n distinct objects. And I ask you the total number of r permutations. What do I mean by r? I mean, for r is a natural number between 1, at most, of course, up to n. We want to answer this one. This is a very extreme important formula that you need to remember it. Of course, the formula will be given to you in the formula sheet. And you also have a button on the calculator calculating r permutations, the number of r permutations. So that is one of those things that you have to remember if you want to solve problems in combinatorics. Now I want you to answer it to me. Instead of having 4 objects, I give you n. You see, I have underlined it 2 times. It's extremely important that the objects that I give to you are distinct. And I'm asking you how many r permutations, the total number of r permutations. What is r? R is any number that you like, of course, between 1 and n. I cannot ask you how many I cannot give you 4 objects and I ask you how many 7 permutations are there. No. So what's the answer to this? Try to modify this again. Can you tell me how many positions do I need? How many positions? Just say something. How many positions do I need? How many positions? R positions. So let me label them. Position number 1, position number 2, position number 3, up to position number R. Because I want to have an R permutation, I have to have R distinct positions. Can you tell me how many ways, how many options are available for filling up number 1, box number 1? N. Because I have n of them available, I can choose whatever I like and put it here. So n options are available for this one. And then the next one is n minus 1. Then let me just write the other one. Position number 3, how many one is left for this? N minus 2. Okay, now I want to ask from you, well, how many are left from that one? Be careful, yes, because usually people answer it wrong. So how many options will be left for the last position? No, there are R, and R in general is smaller than N. Yes, if N is exactly equal to R, then that would be 1. Yes? Yes?
N minus R.
This is usually the answer people say. This is a little, there is 90% correct, 99% correct, 1% wrong. And I don't know why people making the same mistake over and over again. How many numbers are from 1 to 10? Not 10 minus 1. How many times I have repeated this, yes?
N minus R plus 1.
Yes, so that is n minus r plus 1. Yes? Don't make a mistake 2 times, yes? So, do you agree now or not? Yes or no? Yes or no? Okay, so what's the answer then? What is the answer? Let me write the question mark. Okay, so I think your battery is down. So what is the answer now? The answer is n times n minus 1, n minus 2, up to n minus r plus 1. That's your formula. Okay? But this formula is a little bit ugly and hard to remember. Let us use the notion of factorial to make it compact. So how can I write this more beautiful or easier to remember?
I was just thinking n factorial to divide by r factorial, but no.
Not r factorial. Be careful.
N factorial divided by n minus r factorial.
Yes. Exactly. So why? Because if I want to have n factorials, there are some terms missing. To have n factorial, I have to have the product from 1 up to n consecutively. But so it is terminated somewhere. So what I do, I just myself write it like this. So I myself multiply it by the previous number. What is the previous number? 1 unit less. What is the previous number? And then I continue until 3, 2 times 1. But because I have multiplied by this, I have to divide by that one as well. Otherwise, I have changed the problem. Yes? But now if I ask you, what do you see in the numerator? You see the product of numbers from 1 to n consecutively. So that becomes just n factorial. But in the denominator, you see the product of natural numbers consecutively, starting from 1, but ends, what was that? No, this is n minus r, sorry. Up to n minus r. So that is nothing except n minus r factorial. So this is easier, and there is a notation for this number, and that is called p of n and r. So, you see P, permutation, N, the total number of objects, and you have a comma R. I don't know, some calculators write it like this.
And even some books write it like this. And I have seen books write it as a pair of brackets n equipped with an index r. I have seen these notations. But this one is used in your book. Some calculators use this. So this number this is one of those cases that you really don't need to prove it for me. If the answer to the question of the problem is this one, you can motivate it and then you can just write the formula there. You really don't need to answer it. You don't need to prove it every time. First of all, tell me, do you understand what is going on? So if I have n distinct objects and I want to choose a sub-collection of them and arrange them, the total number of arrangements and choices together is taken into account by this single very simple formula. Yes? Okay. So I would say that okay, I will stay here because that's also a very important lesson. And in principle, I have seen students avoid using this. They want to use all the time the product rule, which is doable. But I want you to learn how to use the formula. Of course, if you write always the proof, I will give you the full mark, but I want you to learn how to use the formula effectively. Okay, I think we can stop here and we continue later. Thank you.